Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Since the electrons start from rest, this potential difference gives the electrons a kinetic energy of this value. So this is basically equal to kinetic energy of the electrons. So it is possible to provide this much energy to the hydrogen atom through collisions. Now from the ground state, the maximum energy of the atom, or total Emax or E total, will be equal to the energy at the ground state, or E1, plus the kinetic energy of the electrons. Now we know that at ground state, the energy of the electron is minus 13.6 electron volt, and kinetic energy is basically 12.3. So we get the total energy or maximum energy to be equal to minus 1.3 electron volt. Now from the energy level diagram, figure 27.29, you will see that this atom could be excited to n equals to 3 state. This means the possible transitions the possible transitions when the atom returns to the ground state will be, so let's say this to be an I, and after it returns to the ground state, when the atom returns to the ground state, the possible transitions could be, so n final could be 2, n final could be 1, or it can return to. Okay, so there are other transitions also, so maybe this notation is not a good idea. So let's write all the possible transitions. So this could be n equals to 3 to n equals to 2. We can also have a transition from n equals to 3 to n equals to 1. And maybe the electron doesn't go to n equals to 3 state, maybe it just goes to n equals to 2 state, and then returns to the ground state. So in that case, the possible transition will be from n equals to 2 to n equals to 1. Now we will calculate the wavelength using equation 27.16. And according to this equation, wavelength is given by Hc over the energy of transition. So we have three possible wavelengths here. So lambda for a transition from n equals to 3 to n equals to 2 will be Hc over E3 minus E2. Similarly, lambda for, okay, so let's find E3 and E2. So En is given by, or the energy at the nth level is given by minus 13.6 electron volt. over n square for a hydrogen atom, where n is the state of the electron. So E3 will be equal to minus 13.6 electron volt over 3 square, which is 9, and this gives minus 1.5 electron volt. Similarly, E2 will be negative of 13.6 electron volt over 2 square or 4, and this is equal to negative of 3.4 electron volt. And E1 is basically negative of 13.6 electron volt because n is equals to 1 here. Now let's find the wavelengths that the electron can have. So lambda, when the electron transitions from level 3 to level 2, will be equal to Hc over E3 minus E2. Hc is basically equal to 1240 electron volt times nanometer, and E3 minus E2 will be negative of 1.5 electron volt minus negative of 3.4 electron volt. So this gives lambda to be 650 nanometer. Similarly, lambda 321 will be Hc over E3 minus E1, or 1240 electron volt times nanometer over negative 1.5 electron volt minus negative of 13.6 electron volt. And this gives the wavelength of the electron to be 102 nanometer. And for the last one, when the electron goes from n equals to 2 to n equals to 1, we have Hc over E2 minus E1. This is equal to 1240 electron volt times nanometer over negative 3.4 electron volt minus negative of 13.6 electron volt, and this gives the lambda for this transition to be equal to. So these are all the possible wavelengths the electron can have when it is accelerated through a potential difference of 12.3 electron volt.